Hi, I am Tanuj and I would like to share the details of our recent CVPR work, Hyperbolic Uncertainty Aware Few Shot Incremental Point Cloud Segmentation. Imagine an autonomous system such as Tesla's Optimus humanoid robot, tasked with performing household chores. While the robot can be extensively trained before deployment on a large set of categories for visual recognition, challenges arise when it encounters a novel category after deployment. In such cases, the robot's visual perception algorithms can either be retrained from scratch on the new category samples or fine-tuned using the new data. However, neither of these strategies may be the most efficient. This situation highlights the need for AI agents that can continuously learn from incoming streams of new categories while adapting to changes in data distribution. In this work, we aim to address this novel problem. During the base session, our autonomous system encounters sufficiently labeled samples of various classes, which can be linked to the pre-deployment phase of Optimus. In contrast, during the incremental session, when Optimus has been deployed in a household, the system must be able to learn from streams of novel categories. Furthermore, these new categories may not be abundantly available, so the autonomous system needs to learn effectively from few short labeled data. Hence, the autonomous system needs to tackle the stability plasticity dilemma in the few shot class incremental setup. Although there are methods available for efficiently segmenting 3D point clouds, these techniques struggle to effectively address the stability plasticity dilemma in the context of few shot class incremental learning. Furthermore, most existing methods utilize Euclidean space for segmentation purposes. While this approach may work well for other tasks, we find that Euclidean geometry has significant limitations in effectively representing 3D point cloud data. The flatness of Euclidean spaces fails to capture the hierarchical tree-like structure of 3D point clouds, as highlighted in previous studies. This limitation becomes particularly problematic when there is insufficient labeled data, leading to overfitting and catastrophic forgetting. Hyperbolic geometry is an effective framework for hierarchical data due to its negative curvature and exponential volume growth, which aligns well with tree-like structures. This geometry mitigates issues with class overlap and interference that arise in Euclidean spaces, making it ideal for accommodating incremental classes. However, optimizing embeddings in hyperbolic space can be challenging, especially near the boundary of the point gear ball, where vanishing gradient problems and class encroachment can occur. To address these issues, our model implements a fixed alignment strategy for feature classifier relationships in few-shot class incremental learning. This approach leverages hyperbolic space to maintain class separation and avoid catastrophic forgetting by anchoring classifier prototypes, thus preserving consistency and stability as new classes are introduced. To maintain stable feature classifier alignment, our framework pre-assigns classifier prototypes on the boundary to establish a structured classifier space before backbone training. We enhance margin separation by using hyperbolic ideal prototypes, distributing them uniformly across the point gear ball. Incorporating semantic class knowledge, we ensure distinct separations for closely related classes like chair and sofa. Utilizing the CLIP framework for its superior semantic representations, we query CLIP's text encoder with a photo of a class token to obtain embeddings for predefined classes. By leveraging the homeomorphism between the hyperbolic space and the Euclidean hypersphere, we maximize separation amongst nearest embeddings and enforce orthogonality among ideal prototypes. We optimize ideal prototype positions using a hyperbolic positioning triplet loss inspired by RankNet. Hence, at the end of hyperbolic ideal prototype positioning, we are left with a certain arrangement of ideal prototypes such that the semantically similar ones are farthest away from each other and the adjacent ideal prototypes are orthogonal to each other. For each session, we align the hyperbolic sample mean features with their hyperbolic ideal prototypes of the respective classes using alignment loss. We define the alignment loss using Boozman function and introduce a regularization term quantifying uncertainty of the class features to prevent feature collapse around the ideal prototypes, effectively reducing interference with previously seen classes and vanishing gradient problems. Effectively, the final loss, also known as L-hypo, is a summation of Boozman loss and the uncertainty loss, in addition to the cross-entropy loss for segmentation purpose. Talking about results, our proposed methodology HIPPO consistently outperforms state-of-the-art baselines in almost all of the settings. We show the results on two popular indoor point cloud datasets, S3DIS and ScanNet. We also show qualitative comparison between our proposed methodology HIPPO and state-of-the-art baselines. We observe that HIPPO correctly segmented the wall, while the second-best baseline 3DPC CISS failed to do so. We show qualitative comparison for another setting, namely 7.3T. Thank you everyone. I hope you like our work.